So in this video we will deal with the accelerations of the particle as seen from the ground frame and also as seen from the moving frame. Okay, so this is the ground frame capital XYZ, moving frame small xyz, right, and this is a particle P. This position vector of P with respect to moving frame is rho, position vector of this frame itself from ground frame is r, and position vector of P is small r from the ground frame, and these are the velocities as we have discussed in the last lecture. V capital XYZ, velocity of P from ground frame, V small xyz, velocity of P from moving frame, and this is the velocity of the frame itself plus omega cross rho, and the accelerations of the particles will be A capital XYZ is acceleration of P with respect to ground frame. So that is ddt of V capital XYZ from the ground frame, right. We have to differentiate velocity of the particle V capital XYZ from the ground frame to get absolute acceleration of P, that means the acceleration with respect to ground frame, and small a xyz or A small xyz is acceleration of P with respect to the moving frame. Differentiate its velocity with respect to moving frame, I mean velocity with respect to time from moving frame, this one. So this velocity expression will differentiate it. So that's V capital XYZ equal to V small xyz plus r dot plus omega cross rho. Now we'll differentiate this with respect to time and with respect to ground frame first. Yz equal to this dv small xyz with respect to time, also from capital XYZ, all the terms will be from capital XYZ, from capital XYZ plus also ddt of omega cross rho with respect to capital XYZ. Now I'll break up the terms. This term we'll take one by one. Okay, by the way, this term is A capital XYZ, right. Now this term we can break up into two terms, so that's dv small xyz with respect to time with respect to small xyz plus omega cross v small xyz. This is how we transform differentiation, that derivatives between frames. So that's r double dot. So this is the acceleration of the frame itself, and this term first you have to break it up. You have to break up this term, so that will be d, so d omega dt, so that's this omega dot cross rho plus omega cross d rho dt with respect to capital XYZ. So again see d omega dt, right. So this omega dot is d omega dt with respect to capital XYZ. By the way, so this term also you can break up, so let's write it again. So that's omega dot cross rho. Now we'll break up this term. So omega cross inside d rho dt, so that's d rho dt with respect to small xyz plus omega cross rho, right. Now let's put the things together. I mean all these split up terms. This term is this term, I mean this term is a small xyz, that is acceleration of p from the moving frame. Okay, let's put the things together. So here it is, a capital XYZ is equal to a small xyz plus omega cross v small xyz plus this first term, right? This was the first term, a small xyz plus this. Second term will be r double dot plus r double dot plus this. Third term will be this. Yes, this thing, this whole thing, plus omega dot cross rho plus omega cross write it again, d rho dt with respect to small xyz plus omega cross rho. This was it, right? Now again this, what about this term, this d rho dt with respect to small xyz, this term is v small xyz. Differentiating rho with respect to time from moving frame is velocity of the particle from the moving frame. So this will be a capital XYZ is equal to a small xyz plus this omega cross v small xyz plus r double dot plus omega dot cross rho plus omega cross vxyz plus omega cross rho. So this term appears twice. So a capital XYZ is a small xyz plus this r double dot plus yeah, this is written, okay, omega dot cross rho plus omega cross rho, this one, right? Then what else, plus twice omega cross vxyz. Okay. So suppose m is mass of the particle p. So we will now multiply m with all the terms. Now, if you multiply m into a capital XYZ, that is force. This is the net force as per Newton's law, because the ground frame is the inertial frame. Net force on P. Okay. Now m into a small xyz is the force on P as observed from the moving frame. Right. So there you get, if you multiply, so m a x y z equal to small xyz here plus m r double dot plus m omega dot cross rho plus m omega cross rho plus twice m omega cross v small x y z. Okay. So therefore, see, this is our main thing of interest, that is from the moving frame we observe that this mass into acceleration of particle from moving frame small xyz will give you the force. So this force observed from the moving frame. So this is a real force and plus many terms. So those are the inertial forces or the fictitious forces. So you have so many fictitious forces. See, first is F, this is F, now plus minus m r double dot, this is a fictitious force, plus minus m omega dot cross rho, this is a fictitious force, plus minus m omega cross rho, this is also a fictitious force, and plus minus 2m omega cross v xyz, this is also a force, right? So in high school physics you have learned about this one force, this is only force, right? So in high school physics what we have learned, that this one is the ground frame and there is an accelerating frame. So the acceleration of the frame was this only, as it was translating frame. And if you look at something, an object P, so this was the only pseudo force, the only inertial force, minus m r dot minus, so this was the minus m r double dot, we call it the pseudo force, right? But here you have so many forces, right? Here you have so many forces. So that is the force as observed from moving frame is real force plus how many, 1 2 3 4 types of forces, right? Out of which this force is known as the Coriolis force. We will discuss about the rest of the forces also later on while solving problems in our next videos, but this is a Coriolis force, this last term. So Coriolis force FCOR, Coriolis force is given by that minus 2m omega cross v xyz. So this is a very non-intuitive force actually. So just I will show you one example of Coriolis force, very simple one. Say this, say it's a rotating platform, and say you are standing on this rotating platform, and from the rotating platform itself you throw a ball this way, right? You throw a ball this way. So what will be the direction of the Coriolis force? See, so this is v small xyz, that is, this is velocity of the ball with respect to the rotating frame, right? So the angular velocity vector of this frame is this way, this dot only, omega is a dot, anti-clockwise upward. So this omega cross vxyz will be in this direction. So in place of Coriolis, in the formula of Coriolis force, you have what? Minus 2m omega cross vxyz. So the direction of the Coriolis force will be in this. This is the direction of the Coriolis force. Right, and we'll discuss about this Coriolis force and the rest of the forces details in my next videos, and we'll solve a lot of problems.